Thanks to the organizers for having me out. I come to the title of this talk very humbly. This is a question, not that it's for you and I'm going to answer, but this is a question for all of us to be figuring out. How do we make AI fair? And as we know, some people will say AI is coming. No, AI is here, and it's affecting all of our lives. And as we think about, for example, my little nephew here, it's going to affect a lot of things in his life. It's going to affect which books he gets recommended to read. It's going to affect what music he listens to in his culture. It's going to affect what news he reads. It may also affect the drivers on the road. It may affect what job interviews, what college admissions, all sorts of things about our lives. And what's making people a little uncomfortable about how awesome that is that it's pretty confusing as to who's making all those decisions. So in the old days, like with newspapers, you'd send in a letter to the editor, and there'd be an editor of that newspaper who would decide if that got published, who'd decide what went on the front page, and if you didn't like it, you knew who you could complain to, and you knew who was running things. And there were many different newspapers in the country who were making separate independent decisions, right? But now that sort of has changed. If AI is making the decisions about what news you're seeing, and if more of us are going to the same news sites, all of that scale is happening, and all of that sort of decision-making is being hidden a little bit. And when I first started working at Google, I sort of saw myself as developing tools, ML tools and algorithms that other people would use, and that they would sort of make the decisions about how to use. And I didn't really see myself as being responsible for worrying about things like fairness per se. But what I've realized as a technologist and building ML systems is that we are all responsible. This is a joint problem, because so many of the aspects are things that we control. And there's so many aspects that go into this, and I'm going to get into some of these. Clearly, of course, the training data and how you're selecting and specifying the training data, how you're logging, what you're logging, all this stuff is being controlled by technologists, by engineers, as well as by higher level people. And of course, the inputs that you're using, how you're testing these systems, are loss functions. I'm going to make a case that even the function class you use turns out to be very important to issues of fairness. We'll talk a bit about constraints and how we can use constraints to make models more fair. And of course, just what metrics are we using? What tests are we running before we launch these systems? OK, so is everyone pro-fairness? I'm pro-fair. Everybody pro-fairness? OK. Hopefully, right? So good, we all agree, this is easy. Oh, but wait, it's not really easy. What the heck do we even mean, right? It's really easy to rally behind that big word, but then as we get into the details of what does fairness mean, we end up with a really complicated mess. And a mess that humans have been arguing about and thinking about for thousands of years, dating back to our Greek philosophers who had a lot to say about this. But also, there's societal issues that change what we think is fair. And then this is really an issue of psychology as well. So one of the things that philosophy gives us on this issue is principles and ways of thinking about what might be fair. And a lot of those, as I said, go back to the Greeks. But I'm going to actually talk about a recent principle from John Rawls, his veil of ignorance idea. Surprisingly recent as philosophy goes, right? This is recent work here in 1971. And it's sort of a meta principle that says a good moral principle is one where if you're not born yet and you have to like pick your society and you're like picking your rules, which rules do you want to see that society have before you get to choose who you get to be in that society? Okay, so this is great and that sounds good to me. Okay, but then how do we use this? So there might still be a lot of disagreement about what's fair. Maybe we would all agree, using this principle, that, well, okay, maybe we want equal pay for equal work and that it shouldn't depend on the color of your skin or what gender you are. But now, how do we actually do that algorithmically? How do we actually impose that principle on our systems? So one aspect is maybe we say, okay, let's just make sure that there's no inputs about these features. This is called fairness through unawareness. And as you might expect, this sort of just isn't strong enough, right? There's going to be a lot of correlated features in the housing market that we talk about redlining by zip codes and stuff that just make this hard. I may not know how old you are, but if I know what music you like, I bet I can guess a lot about your age. And the training data labels that we work with may be explicitly biased. So if we're like worrying about how much to pay people, if we just reflect the training data, maybe it's already sort of too late. And even when they're not explicitly biased, there may be implicit biases. In some groundmark work by Cote and Laurie back in 1993, they point out that if you pay people less for a job, they may do a less good job. So if you've got two groups, one a group who you're systematically underpaying, they may be systematically underperforming as well, because they're like, oh, I'm not getting the big bucks, why should I put in the effort? So all of this confuses our notion of training data. Okay, so that's some of the stuff that philosophy's bringing to the table, but I also want to emphasize how complicated fairness is from a psychological perspective. And starting back again with philosopher David Hume, he pointed out that different people have different moral sensitivities. Some of us literally feel injustice more strongly than others. And not only is injustice something that we feel, we may have different notions of what we mean by fairness. And Jonathan Haidt, in his 2012 book, sort of sketches out sort of 5 to 7 distinct moral dimensions that you might feel injustice about. Some of them are simple things like, hey, it's not okay to harm other people. But a couple of them have to do sort of more directly with fairness. And at least 2 distinct ones are sort of, do we care about equal outcomes? Should everybody have an equal likelihood of getting a free lunch? Or do we care about equal opportunity? Everybody should have a fair chance to fish for their lunch. Now, from a statistical point of view, we'll sort of think of that as, okay, if we have some different groups, are we worried about, say, in a classification setting, making sure that the probability that people get a positive class is equivalent across the different groups? Or do we want to condition that on whether or not they deserve to have a positive label? So equally deserving people from different groups are getting positive labels. And one of the things I'll keep coming back to is you'll notice that the second criteria here, equal opportunity, is conditioned on the training label. So now how good our training labels are becomes a really important part of this question. So if we're starting with already biased or incorrect or poorly sampled training labels and training data, we may already be too late to apply that principle. Okay, and we can think about sort of those 2 fairness issues in a different way as well if we think about how they relate to reality. So one principle is, hey, when we build AI systems, they shouldn't distort reality. So for example, if you search for coffee near Stanford, one of the things that we try to do on maps is not just serve you the big chains, which is really easy for us to do, but try to find the local coffee shops that are high quality coffee shops as well. Because local businesses also should be having a shot at being shown, and that's reality, right? There's local businesses, and that's only fair. So this sounds pretty good, and for a long time I was like, yeah, we shouldn't distort reality, that's just how it goes. But the counter argument is that, reality isn't fair. AI is very powerful, it's changing our world, and we have a chance to change the world for the better. We have a chance to think through all of these issues and try to make sure that our AI systems are making the world a better place, whether that's making it more consistent with law or policy or justice. But again, these words, justice, equality, the law, they're very easy to say. They're much harder to execute the details of in technical systems and to agree on the details. Okay, so we've talked a bit about what does fairness mean, finding the right policy. I don't have any good answers for you other than, hey, it's really complicated and you need to think really hard and you want to get information and opinions from a lot of stakeholders about what might be considered fair or what might be issues in your system. And of course, the most important thing you can do is get great training data and worry about the quality of your training data and whether it reflects what you're looking for. And then what's perhaps a little surprising to people is that there's a lot more we can do on the machine learning side apart from the data to help make things fair in general. Okay, so at this point you might be thinking, okay, this is all really interesting and I'm glad that someone else is worrying about these things, but it's not going to be a problem for me. I'm just going to get fairly sampled data, I'm going to do this problem, everything's going to be fine. So let's just highlight a few of the ways in which just even really simple systems can go badly. And I'm being a little too vague here by saying bad classifiers, but how good people can train classifiers that don't really work as well as they might expect in some simple ways. And this is just going to be an incomplete sort of version of 3 or 4 other things to watch out for. So our first one here is just data disparity. So if I want to predict if you like an artist, it's much easier to predict if you like Van Gogh than it is to predict if you like the Japanese artist Bokuyo. I just don't have as much data about whether people like Bokuyo as I do about Van Gogh. So it's just much easier to be accurate and to do higher quality job with majority classes. Okay, so that sort of suggests that all we need to do is make sure that we sample minority classes more. But even if we do equal sampling, and even if we put equal effort into building good classification systems, we may not get equal outcomes, in part because different problems are just harder or easier than each other. And we have to be real about that and investigate that. As one example of that from Google, we'd like our Google mapping systems to work equally well around the world. But we have to put a lot of effort into getting them to work well in India because India doesn't have a formal address system. So when you want to go to this temple, the address on the books is its opposite Red Fort. That's a very, very vague notion. So it's just a harder problem, and that means more work has to go in order to make it as accurate as the rest of the system. Okay, for this next one, we need some audience participation. Can anybody tell what animal this is? Okay, I'm hearing a lot of dolphins. This poor creature washed up in Moss Beach in the Fitzgerald Marine Reserve. This is us helping a ranger drag it off. And it is not a dolphin. It is a porpoise, which is my point. Labelers are often less good at labeling minority classes or minority labels that they don't have much experience with. Now, to really hit this point home, do you know how this dolphin died, or how this porpoise died? Exactly. So this porpoise was killed by a dolphin. So, you know, here we're just dealing with sea creatures, but if we'd been dealing with like labeling people and we mistaken someone for their murder, we'd be very unhappy. Okay, but so this is a problem that the quality of your labels may really differ and may really vary across your different classes, even if you've worked hard to get good labels. Okay, then transitioning from thinking about the data to thinking more about the modeling, of course we need the right features, and different subgroups or different classes may need different kinds of features to do a good job, and they might need different expressibility, they might need different feature interactions, or different flexibility to the model. Okay, so what else can we do here? So we have the training data, and that's usually how we control machine learning algorithms. But our team has done a lot of work in sort of saying, well, what else can we do to take policy goals, translate them into math, and take them into the training algorithm? And one set of these kind of goals is to constrain the output statistics. And we foreshadowed that a little earlier in this talk. We'll call these rate constraints. One example of that is we might say, for example, I'm going to train a classifier. It's got to work everywhere in the world. And I'd like it to be roughly as accurate in India as it is in the US. So how might we do that? Well, we can set that up as a constrained training problem. So we might minimize our classification errors. And we might just add a constraint on the accuracy on the one subgroup compared to the accuracy on the other subgroup. Okay, so that sounds great, but what if what my classifier is doing is giving out free lunches? Then the people in India and the US might not feel this is strong enough. They might really want equal benefits, and they might feel that that's a better notion of fairness, is that they're more likely to get positive classification labels at the same rates. They may not really care if my classifier is accurate. They want the free lunches. And we might feel, well, that's not really fair. Really, we should only worry about, are we giving equal lunches or free lunches equally to people who deserve them, to the ones labeled positive in each of the countries. But there again, we have this challenge of, did we get good training data? Can we trust that those labels are right in the first place? And then lastly, one of the things that we see a lot in practice is that these types of constraints may be a bit too difficult to do, but we may at least be able to make sure that people are not losing out. Because usually decisions are already being made, whether it's by an AI system or in the real world. And we could say, let's launch a new decision-making system. Let's make sure that people are not losing benefits or that the system is not less accurate for them, right? We want things to help everyone. Maybe some people are going to get a bigger improvement than others, but let's not make things worse for some subgroup. Okay, so we now have 4 different statistical definitions. These are constraints on the output of our classifier. They contradict each other. They may not have they may not even be feasible. So this is all sort of just to emphasize the complexity of it's not always clear what you want to do or what is going to be the right thing. However, the good news is, algorithmically, these are all sort of the same beast, or they're at least similar beasts, which is we can write them all mathematically somewhat the same. So they're all constraints on the classifier's rates. We can write all of those issues as whether it's a positive rate on a data set D or the negative rate of the classifier on the data set D. So just for example, if I wanted to constrain the recall in India, I can just say that the positive rate on the class of India has to be greater than or equal to 70%. And in fact, any of those different fairness notions I was telling you about, we can write in this form here, which is a linear combination of positive and negative rates. So this is nice from the algorithmic and mathematical point of view, because we can now sort of just set up one general type of problem and figure out how to solve it, which is that we want to take our usual structural risk minimization problem and add in rate constraints to impose whatever these kind of fairness constraints are that you'd like to have. Okay, we could talk a lot about why that's hard and why it's interesting. I'm just going to point you to a couple papers. There's been a bunch of research groups working in this area. I'm selfishly going to point you to our most recent paper, which does survey a lot of that related work as well. This is a journal paper. It's on arXiv now. It'll appear in JMLR. And part of the trick here is that these are non-differentiable constraints. And there's a lot of theory to getting this to work right. This actually, the theory paper here won the best paper award at ALT. And there's a TensorFlow library, so you can play around with this yourself if you just want to give this stuff a try or use it as a base for your own research. OK, so wow, that sounds great. We've totally solved this. All you have to do is pick your fairness policy, pick your groups, and we're done, right? Of course not. OK, so a lot of challenges with this as a solution. So let me just go through some of them. The first challenge is if you have small groups. So maybe you have 1 million people in your training set, but now you want to make a constraint about Alaskans. Suddenly we don't have so many people. We're going to have statistical significance problems. We're going to have feasibility problems. And if you start doing intersectional groups and you worry about the Alaskan women over 80, this is also going to get pretty hard. You're now trying to make a constraint on 5 examples. And just because you satisfy these constraints in your training data, might not really pass, might not generalize to your test data. Just so we have generalization problems in machine learning, we're going to have generalization problems with these constraints. And then lastly, I haven't really handled how do you handle things that are continuous, things like age, et cetera. OK, well, those are just some of the statistical and algorithmic challenges. Bigger challenges, we may not have the data to do this at all, right? Maybe I want to make sure that my system works equally well for cat lovers and dog lovers, and I don't know who likes cats or dogs. Maybe my system doesn't store any information about race or gender, and I don't want to go near it. All sorts of problems can happen there. We've done a little bit of work trying to look at correlated groups and saying, well, we'd like to make sure the system is fair for age, so maybe we can make it fair for people who like different kinds of music and see if that transitions over. A lot of interesting questions there to see if that can really work well. But I think the biggest problem with this rate constraint approach is that it's about sort of categories and about groups and about distilling us down to one feature or a few number of features. And really, we're individuals, and fairness is about sort of our individual experience. I mean, it's nice if my people, however you define that, are getting an average statistically good experience, but I personally want fairness for me, right? So what does that even mean, and how do we impose that? So we can look at that as well. So one of the first principles to get some traction in the machine learning literature was from Dwork, suggesting that we should make sure that similar individuals do get similar outcomes from our systems. And of course, if you have a binary classifier, you're like, well, there's going to be a decision boundary. But this kind of does imply that mathematically, one of the things we can do is prefer smoother function classes and prefer smoothness regularizers, that if we're not sacrificing too much accuracy, we can at least make sure that things are a little bit smoother out there for individual experiences. This next policy, I'm going to dig a little bit more deeply into, which is that sometimes there's inputs that we shouldn't be rewarding or penalizing. So let's look at an example of that. So yeah, do people feel like one of these classifiers is fair? Let's pretend we're trying to do college admissions. We'll leave out the input of how much money your parents give to. OK, what do people think? How many people like the classifier? This one on the right, fair, or decision tree classifier? And I've got this classifier on the left, some nonlinear algorithm. This is a toy example, but pretend it could be a DNN. OK. So what if I showed you two individuals, x1 here in green and x2 in red, who's not getting admitted to this college? Does this feel fair to them? No, x2 is getting penalized for having a higher SAT score, even though he's got the same GPA. So that's a pretty bad individual experience. And this is a very easy thing for algorithms and for our models to do, is overfit in this way that basically violates basic monotonicity constraints that we would think of as fair. So here's an example of the same thing, but with some data from a UCI data set. This is for credit scoring. Here we've got 24,000 examples in 2 dimensions. I'm just going to look at 2 features here. Are you single or married, and how long has it been since you paid your bills? So 24,000 examples, this is plenty of data. I shouldn't have any problems with overfitting, right? But what happens is, what we're seeing here, is the mean and the variance, or the confidence intervals of the data. Most people pay their bills pretty fast, so that data has pretty good confidence. But there's not many people out here who haven't paid their bills for a long time, so we're getting very noisy data in that part of the space. So even though we have lots of training data, this is a big data scenario, once you start looking at small parts of the space, it still ends up sparse. We have the same problems we've been having for 50 years, which is we don't have enough data, and we're going to get overfitting. In fact, if we fit a model to this, and we fit just a nonlinear model, it's very likely we'll get something like this. And what is this model doing? It's saying, hey, we were going to give you a pretty good, predict your default rate as pretty high if you didn't pay your bill for 3 months, but if you just wait longer to pay your bills, your default prediction rate will go down. Awesome, yeah. I don't want to live in this society, right? That doesn't feel very fair. So what can we do? Well, we can impose constraints on our models. And one thing we can do is impose monotonicity constraints. And this requires us to look at our features and think a little carefully about whether that makes sense or not. In this case, I think it would make sense. And if you do this, you don't really gain or lose any test accuracy in this case. You gain a little bit of test accuracy, but not much because there's not many examples out there. But it's about guaranteeing that your model is behaving fairly throughout the space. And more generally, we can use these sort of monotonicity constraints to make sure that we don't penalize or reward inputs in ways that don't make sense from a fairness perspective. And usually these constraints are done in a way where if you only hold all the other inputs fixed. And this might seem familiar to some people. This is an old idea in the statistics literature, just as a matter of regularization. People may be familiar with isotonic regression, which is an algorithm for doing this in 1D. There's also been a lot of work in monotonic neural networks. And our team has done a lot of work in monotonic lattice models. This work by Velikova in 2010 sort of points out that monotonic neural networks really lose a lot of expressibility and have some theoretical problems. And so we've been working on a different kind of modeling using lattice models. There's a series of papers on that, but I'll just point you to one of the more recent ones, deep lattice networks. And there's a TensorFlow package that lets you play with these models. And I'll talk about this for a couple minutes. In order to make this work and to be able to get those kind of shape constraints, like monotonicity, underneath the toolbox, the layers are using interpolated lookup tables rather than using, say, ReLU layers. So a 1D interpolated lookup table is just a piecewise linear function you see in the back of your math textbooks. A multidimensional lookup table just spans the space, and again, you can interpolate and get a function that looks like that. And the toolbox lets you sort of go the whole span of flexibility, from linear models to generalized additive models, all the way to these sort of deep lattice networks, and you can plug and play with other layers in TensorFlow. Okay, so apart from letting you have these monotonicity guarantees, which may in some cases be useful for fairness, these models also provide some smoothness. And this one's a little harder and a little more subtle. But if we now just look at these two algorithms, so I've got a decision tree in the one case and a linear model in the other, which society do you want to live in? Which society do you think is a fair or better society? So I think we could and maybe should disagree on this. Personally, I would rather live in this society over here because I feel like it continues to reward people for hard work. That if you get a higher GPA, you don't have to do quite as well as your SAT. Whereas this society kind of suggests that, well, just do the minimum and you'll be fine. And that doesn't seem fair to the hard workers and the people who put in the extra effort. But that's sort of a second order subtle effect compared to the, wow, one guy's getting penalized for having a higher SAT, where it's like an obvious, I think, a badness. Okay, so yeah, we've talked about just how complicated these policy goals are, but I think there is stuff we can do and there's stuff we can agree on and we can find ways to make society better. We do need to most and foremost worry about having the right data, but we can do a lot when we worry about our algorithms and our algorithm choices as well on top of that. And I've only touched on just a small set of aspects here. There's been a vibrant machine learning fairness community that's been working and raising awareness about these problems for a few years, and you can find a lot of literature. It's sort of like Mad Libs. You know, you pick your name and you pick fair and put it into scholar.google, and you'll probably find some papers of some people trying to think through these problems, and encourage you to think through them as well. One specific thing you can do if you want to get involved is check out this new Kaggle competition run by Google's Conversation AI team, where we're challenging people to help identify toxic comments. This contest just started. The deadline's in 3 months, so you still have plenty of time. You're not behind if you wanted to jump in and give this a try or just play with the data. And to conclude, we really do have a huge opportunity here. I think a lot of people are worried about AI. They're worried about the risks. But on the flip side, I'm excited about AI. I'm excited about the possibilities. We really can sort of bring fairness at scale. We can move society faster in good directions. But that said, it's really complicated, and we need different viewpoints because don't expect everyone to agree on some of these issues and about how to execute them. And lastly, it's really up to us. This isn't something that someone else is going to take care of. This isn't something that the business person or the VP or the program manager does. This is something that our decisions and our research and our minor choices does end up affecting. Okay, thank you.
Thanks. We have time for a few questions. If you want to ask any questions, just line up behind the microphone.
Hi, Marco Canini from CAUST. So this was a very sensational talk. Thank you very much. My question is regarding essentially what we intend by AI today, which seems to be fairly conflated with machine learning, given all the recent successes. Do you think that there is something beyond, basically, this notion of AI equal to machine learning when it comes down to fairness, in particular with regard to the more traditional AI techniques that made use of logic and rules and so on? And would that perhaps be also an approach that is worth pursuing? Because at that point, there is a more interpretable, more explainable way of understanding what decisions are being taken by AI.
I think that's a great question, but a very hard one. And you're right, I have conflated AI with machine learning in many ways because it's what we know how to do. And the problems are already really difficult for machine learning. As we move to more complicated AI systems, I think they get even harder. One of the things I would say is that when you have more of an end-to-end system or a system with many repeated plays, then that does change the notion of what makes the system fair and how do we deal with that. There's been just the start of some research in that area. That I can't remember quite the reference on, but people are just starting to look at what happens in these larger, more complicated end-to-end systems for fairness.
Thank you.
Hi, Michael from Amazon. Thank you for your talk today. I was curious what you would say as AI is becoming more popular, and I think even at this conference, there are people talking about ML as a service, being able to offer kind of AI in a boxed way or as a service. Just curious, how do you think about or the concerns for fairness in that model?
I think it's a real challenge. So I do work for Google, and we try to build products for everyone. A lot of startups and smaller companies don't have that same responsibility or expectation, and they may be building products that are specifically only designed to work for a small set of people. So the assumptions there about how well does your product need to work and for what large a group may be different. But I think that, well, it's easy to worry that as we have everybody using AI, that not everyone will use it wisely because it's such a powerful tool. But I think we can attempt to just educate ourselves and demand from just socially from our peers that we're worrying about these issues and that we're at least thinking them through and being honest about them with ourselves.
Sure. Let me clarify the question now that you've answered that well. Do you think the responsibility, if you had to pick a side, do you think the responsibility falls more on the service provider or the user whose training models may be providing data but not aware of the internals?
Okay, so I think you're saying, well, if we're giving AI as a service and people are using it, what happens? I think with many questions about AI, it's not that different to things we already have. For example, if you're already providing cloud services and you're providing compute power, how responsible are you for how that's being used, right? If you're, and some of this comes down to, if you have a dog and the dog bites a man, how responsible for you is this? So I don't know all the details there, but I do think that making analogies to problems that we already have and legal solutions we already have is probably the best way forward for society because it'll be easiest for us all to agree if we can rely on precedent.
Thank you so much.
Okay, maybe, yeah, one last question.
Sure. You kind of started to touch on the fact that there's, oh, sorry, I'm Roseman from Spotify. You started to touch on the fact that there's some literature around this idea, but how do you reason about this idea of monotonicity when you have like very complex features like embedding vectors and things like that?
Yeah, so definitely monotonicity is easiest if you have semantically meaningful inputs, like how long since they paid their bills, and then you can constrain the output to have that relationship. If instead you have very sparse inputs, like zip codes, and you throw it into an embedding, yeah, your life is hard. And I don't have great solutions for that. So as I said, this is a humble talk here in terms of how do we make AI fair. I think we have some partial solutions and some good ideas and some stuff that works sometimes, and we're just going to need more work.
All right, great. Let's thank our speaker one more time.